Okay, thank you so much for joining. This is Exploratory Online Seminar number 92. Today, I'd like to do introduction to ANOVA, which is a statistical test or hypothesis test. This is a part one-way ANOVA. So I'm gonna start with today, and then maybe like another couple more to kind of explore this area of ANOVA analysis. Okay. So let me introduce myself. My name is Kan Nishida, CEO, co-founder at Exploratory. We started Exploratory 2016. Since then, we've been building Exploratory as a tool and also providing this type of seminar and training to democratize data science. Our vision is that data-informed decision-making is a key to make the world better. And therefore, we like to democratize data science so that anybody can use various methods of data science and apply it to their data. And then they can find useful insights, and then they can make better decisions for themselves. When we say the data science, we use this sort of like a workflow map that you usually use, start with a question, business questions, or whatever the question you have. And then like you want to access the data, and then you transform the data, then you visualize or analyze the data with various analytics methods. Then you can find the useful insights from the data, or you can validate, whatever the hypothesis you have, you had before. And then like once you find some useful insights or any confirmation, the validation, whatever, and then usually like you want to communicate with other people so that you can make a decision as a team or in a collaborative way. So that's a communication at the very right-hand side. So Exploratory provides these 5 steps, like data access, data wrangling, visualization, analytics, and communication through the modern and simple UI to make it easier for anybody to understand their data better. Okay, enough about the introduction. So let's get into today's seminar. So online seminar number 92. Today, the topic is Introduction to ANOVA, part 1. A one-way ANOVA. There are like other type of ANOVA. So like, for example, such as like a two-way ANOVA or uncover or repeated measures, various other things. But today I like to focus on this so introductory. So what is really the ANOVA? So by using one-way ANOVA. Okay. So, but before getting into, I have done like a couple of other hypothesis testing seminar. So you can find past recordings through our website. Go to exploratory.io, and under the Learn menu, there's a training seminar. When you click on that, then you get to online seminar page. At the bottom of the page, there's a link to the past recording. When you click that, you get a list of the past recording. There you can find a bunch of like a past recording, but also like see a set of hypothesis testing related ones. So for example, this introduction to hypothesis testing, this is actually like if you're not familiar with hypothesis testing or statistical tests, I strongly encourage you to take a look at this video first, so that you can understand the basic framework or the thinking framework, why you have to think this way to test the hypothesis, why you have to build this hypothesis in a certain way, that type of thing. So once you have done that, then there are other hypothesis testing, like such as t-test or chi-square test and Wilcox and classical words and other stuff. And then we have recordings for those. Only thing we don't have the recording yet is, of course, the topic of today is ANOVA. Okay, so the really hypothesis testing is like when you see the difference, and the question is that difference is significant? Is that something like you need to pay attention to? Or it might be like marginal, it's just a random difference. So like you don't have to spend much time on it, like you should move on. So that's the kind of key question like you often face, especially in the business environment. So in order for you to be able to answer, you can run hypothesis tests. Hypothesis tests, okay. So ANOVA. So statistical test for the comparing the multiple means. Because this multiple means there's another type of the hypothesis test, another hypothesis test method called t-test, which is very similar in terms of like the kind of purpose or the goal. But a t-test can be used only for comparing two means. Like when you have two groups, that means you have two means. You can compare those. That you can test the difference is significant or not. ANOVA is for when you have multiple groups, more than two. Can be used for two too, but also 2, 3, 4, 5, 6, and multiple groups. Okay, so for example, we have this data about a school score, like let's say like student score, whatever the topic could be, like mathematics or like a language or whatever. And then we have ABC 3 schools. Okay, each row is each student in corresponding school. Okay, so we have these scores, and then we calculate the mean or average for each school. So now like we have different means here, right? So then the question is, are these differences significant? Because if it's significant difference, then from here, like we can say, oh, well, school B is better than school A and C, and school C is the worst among these schools, right? But can we make that kind of decisions or judgment or not, right? So when you, I plot these scores with a bar chart. And when you look at, when you're using the chart and kind of exploring the data, you see this kind of chart often. And again, the question is this something that I should look deeper in this thing? And then to test that, basically what you want to know is this difference significant or not? That's where you get into hypothesis test. Hypothesis test has sort of like a framework, like for the detail, you can watch the introduction to hypothesis testing recording. But I'm gonna just cover this a little quick. So basically think of it like you have like a two systems of thinking. One is a deduction, another one is an induction. Deduction is like you start with this assumption, something about like sort of universal truths that like everybody can agree on. Then from there, you can logically construct a conclusion. And that can be used to explain what is happening in the world or why that things are the way they are. Right. So and the induction that's the opposite side. That's actually start from the bottom. So you observe the world, what is happening, and you collect a bunch of like observations, and then based on that, you build the theory or conclusion by using the probability. So it's always the conclusion or the theory, whatever come up with is always estimation based on the probability. Okay, so the direction is different. Okay, either start from the theory or kind of like a thinking in the brain or mathematical side of things. That's a deduction. Induction is like based on your experience or like what you see. Then you build something like a theory or something in the thinking in the brain. So the direction is a completely opposite way. But in real world, basically like how we learn things is usually this iterative learning process, through iterative learning process. This is not like I came up with, this is actually like George Box, who is a great statistician from UK. He back in the day, like he was kind of just showing this diagram. So basically, like you start with the data and so like induction, but then you came up with like a theory. But that theory itself, like you want to actually deduce and then check with the data. And then from the data, you build the theory, and then like from the theory, like you do the so going back and forth, induction, deduction. So what does this really mean? So when you do the hypothesis test, you need to establish what would be the hypothesis. So typically, the alternative hypothesis is something that like the typical hypothesis you have. That in this case, are they different? That's what you want to see. You see the difference, by bar chart or whatever. So like your question is, are they same or no? Like I'm seeing something different. So is this different? But in order to do the hypothesis test, you need to have the hypothesis that you can disprove. That is called null hypothesis. Null hypothesis, in a simple term, it's basically there's no relationship. It's all equal. The difference is zero type of hypothesis. So it is true that mean of school A, equal mean of school B, mean of C, those are all same. That's a null hypothesis. And then basically, like we use the data and the probability to test this hypothesis. Either we reject or accept. What that mean? So again, let's start with the deduction. Okay, so the basic hypothesis or assumption here is that no difference among ABC schools. And if that is true, we can build logically construct to the conclusion, lead conclusion. There might be a bit of difference, right? In this world, there's some, always there's a variance, but that difference will be very small to the point that we can move on. It's a marginal difference. Or in a more like statistical, let's use a statistical word a little bit here. The difference can be expressed by the statistical value f. We can calculate that difference for somehow. I'm going to cover that later, just in a minute. And but the f value, this value f can be explained by the probability. Meaning, like it just can't be just sort of like explained by randomness, or by using the probability that like, oh, that's just sort of like a expected difference or something. Okay, but then so that's the deduction side. So now moving to the observation side or induction of the world, then we look at the data. The world is actually the data. Then we can calculate the f value based on the data. And then once we get the data, we can also calculate the p value or p value. The p value really is that like what is the chance of getting the f value, assuming that null hypothesis is correct, the left-hand side is correct. Then what is the chance that we get this type of the f value? Okay, so what is this like a p-value thing? What is the threshold? What's the 10% is enough, or 5% is small enough? Where is that? So it's like how did it happen or can happen? Where is the difference? There's no like objective logic behind this, but typically like in this world, like people use like a 5%, 1%, 0.1%. These three values are kind of typical. That doesn't mean like you can't use 2%, you can't use 0.01%, you can't use 10%, but it's just typically like, these are the three values you see often, especially the 5%. That's if you're not sure about like where to set this significant level, I recommend you start with 5% and then slightly adjust as you move forward. So let's say like we're going to take the 5%. So basically what we're saying is like less than 5% is basically like unlikely, right? It's like an unlikely event. Greater than 5% is something can happen. Think about it like weather. If it's a 10% chance of the raining and then rain, you can maybe accept that. It's like, 10% chance, still might rain. But if somebody said like 1% chance for raining and then rain, and you'll be like, hey, what is going on? Maybe this weather forecast system is something wrong or something, right? So that type of threshold. So if we set the 5% or 0.05, the p-value is greater than 0.05, so meaning it can be 10%, 20%, 50%, 80% chance of things. Then what happens, the right-hand side, bottom, the statistical value is f, and then the chance of getting this value is greater than 5%. So that means left-hand side, the null hypothesis of the world, the deduction world, is a world of theory, and the world of reality, right-hand side, is consistent. Okay, so something like based on like there's no difference between A, B, C, and then like we see some difference and calculate the f to represent that difference. But the chance of getting f is like even if the null hypothesis is correct, you can get that like a 10% chance. So like that can happen by chance or by randomness. So it's consistent. Okay, so therefore what we're going to do is we're going to accept the null hypothesis, and then we're going to keep going. So that means like no evidence to support there is a difference. So no difference. Okay, so now what happened like if the p-value is less than 0.05 or 5%? That case, these two worlds are inconsistent. Left-hand side, the world of theory, is based on a null hypothesis of like no difference between A, B, C. If that's the case, then right-hand side bottom, let's say like we get like a 5% chance of seeing this F. That means it's like unlikely things is happening. right? If you want to make it like it's super easier to think, it's like not just 5%, you can say 0.0001%. It's very small value or something like that, which means basically like it's just impossible to happen, almost like impossible to happen. But it's happening in the real world. So there's got to be something wrong in the theory, which is a null hypothesis in this case. Therefore, we can reject the null hypothesis, and then we conclude the opposite. So in this case, there is a significant difference among A, B, and C. We're not talking about like a small, like a 5 points difference or 10 points difference, but it's just like some difference is something that we need to pay attention to instead of let's move on. And that's what we mean by significant difference here. Okay, so that's the basic framework for like ANOVA, or in general, like a hypothesis testing. I use F value there, so that's why it's more kind of gearing towards the F value. But now they're going to how to get this F value or even P value. For that, we need to get into the variance thing. ANOVA stands for analysis of variance, so it's really about the variance. Okay, so what is variance? I'm going to just kind of cover a little basic of the variance, just in case you're not familiar with variance. So when you have like an employee, like a A, B, C, D, E, F, G, and then like we have like ages of those employee. Okay, and the right-hand side, like I kind of like plotted, x-axis is an A, B, C, D employee ID, y-axis is the age. Okay, and each employee will be represented by the orange dots, okay? And now like we draw this mean or average age, which is 38 years old, okay? So in order to calculate the average, you add them up and then divide it by, we have a 7 employee here, so divided by 7 equals 38. Now, in order to see like what's the kind of sort of like what is that like a mean difference among these people, or like in this case a difference, but like we want to see like what's the variance in this case. Then first what you want to do is like how much of the difference from the overall mean, okay, and then we calculate for each employee. So like some employees like minus 16, some employees happen to be on the average age 38, so therefore the difference is 0. But anyway, so we calculate all of them. And what we want to do is basically we want to calculate the mean of these differences so that we can say, oh, in average, these people are like, differ from each other for like about this much, and precisely differ from the overall mean. But we can say like if this, we want to basically have the one value to represent the sort of like a variance, a variety within a group, okay? And then now, what we want to do is we want to calculate the mean of this, but the problem is if we add them up, it becomes 0. Difference from the mean, in theory, like we add them up and then it tend to become 0 or it's close to 0. Okay, so then the problem, then we can't even calculate the mean because we can, 0 divided by any value, in this case 7, always 0. So what we do is actually, before calculating the mean, why don't we just square them? So minus 16 become 256, positive 256, not minus. So all the value become positive, even like a negative value when you square them become positive. And then once we get these values, then we can add them up and then divide it by 7, which is the number of employee. And then you can calculate the average or mean, in this case, 153.14. And this number is the variance. Okay, but then this number is kind of weird because like you square them up and then, so what is 153.14? So in real world, you can't really use this number because nobody understands what that means really because it's squared. So typically what we do is we we take the square root of the variance. Then we can do the opposite of a square and then bring this, for example, in this case, a 12.37 something. And then now this number has the unit of the original value, in this case, age. So when you see 12, that means 12 years old. So in average, all these employees were like 20 years apart from the overall mean. Okay, so then this number is called standard deviation. So you might have heard of the standard deviation, but standard deviation is basically after you take the square root of the variance. Okay, so either way, the variance is actually squared value. The standard deviation is not, but it's still both of them basically what they are really trying to say express is the variance in data. Okay. So now think of it as like once you get the standard deviation, so you can say like, basically most of the values are within this range. Most meaning not like 90% or 80%. It's just like an average, all the values resides in this area can be, like 60% or something like that. And then basically, like when you get this number, typically you use it to compare among different groups. Okay, so like you have ABC, then you can say like, one group is standard deviation is 2, another one is 5, and then you can say, oh, you know what, like one group's variance is smaller than the other. Okay, so that's a variance in a nutshell. I kind of mix up the standard deviation variance. In this analysis, we're going to use the variance. ANOVA is really about the variance, but basically the same thing. The important thing is how you can express the variability in data with a number. Okay, so let's take a look at the variance. So for example, in this data, I brought all the students numbers, scores on this chart. School A, school B, school C. Okay, and then the total variance is basically, you remember, like first you calculate the overall mean, and then calculate the difference for all of these students, and then they square them up and take the average of that. So that's the total variance. Okay, but this total variance can be decomposed to two type of the variance. One is the variance between, the other one is the variance within. So this between and within, this will be the key for understanding the F value or even like ANOVA. Okay, so let's start with variance between, what this one really means. So we have means, right? So school A, school B, school C's mean scores 77.4, 80, and 72.1. And then we get the overall mean turn out to be 76.5. Okay. So the variance between is about these three values. What that means is, so now we want to understand like how, what's the variability among these three, just the three. Yeah. So then we take the difference between the means, each means, and the overall mean. So we calculate the three different numbers, right? Then from there, we can calculate the variance. So it's, square them up and then divide by, in this case, 3, and so on. So now like we have this like a red color, that's the variance among these three differences. Okay, so that's a variance between. So variance between means variance between groups A, B, C in this case. Okay, so now another one is called variance within. But what is within? Within is basically that within each group. So in the A, in the B, inside C. So what's the variance for each group? Okay, so to calculate that, like we need to calculate the mean for each group, not the overall, but the mean for each group. In a group A, B, C, we have three mean, which is basically the one like we use when we are working on variance between. Okay, and once we got get these numbers, then we calculate. Let's focus on school A, the green color. Then we have like 10 people, 10 students. So we can calculate the differences, the 10 differences for each student compared to the 77.4, which is the mean of this group, this school. Do the same thing for B, do the same thing for C. And then once you get those differences, and we square them up and then divide by the number to get the average. Okay, so that's that. So I use that dotted vertical line. Those are like a basic variance within each group. Okay, so at this point, so I'm going to just focus on this like a variance within here and bring the variance between, which is the red color. Okay, so we have like two different kind of variances here. we're going to separate these two. Okay, so left-hand side, what we are seeing the variance between, okay, between the groups is mean of A, mean of B, mean of C, and then we just calculate, we want to see what the variance between or among these means, okay? And the right-hand side, the variance within each group. And then when we look at these two, what is the ratio of the variance? So let's say variance between with the left-hand side divided by variance within. Then we can basically compare which one is bigger. So in this case, it's almost like the same, but it's slightly like variance within right-hand side is bigger. So that means, okay, so variance between is less than variance within right-hand side. That means like a variance between is relatively smaller. So the difference, there's a difference here among the means between school A, B, C, but when you compare to the variance within each group, that difference is not that big, right? That's how you want to think about when you want to when you compare the three means among three groups. Okay, and obviously you want to have this variance between to be bigger than the variance within. Then you can say, okay, maybe there's not much of a variance in this data, but we have this means a difference between the means is pretty big. So therefore, like we can consider this variance is pretty significantly big or not, right? So that's basically, this is the key part of the ANOVA. Okay, so let's take a look at then the opposite case, right? So how about like variances within is pretty small. So there's not much variance within each group. Then, so let's start with variance between the means. These are the same as before, okay? And then the red color, the arrow vertical line represent the variance between or variance among three schools, okay? And now variance within is pretty small in this example. Like I made it super small. So all the students in each group are pretty much around the mean of each group. Okay. When you look at the all entire data, the variance among, total variance still, pretty big. But when you take the mean of each group and then, separate into three groups, and then the variance within that group is pretty small. Okay, so in this case, what's happening is compared to variance between and variance within, and it become something like this. Okay, and then now let's take a look at the ratio. And can't you see now here is like a left-hand side, the red color line or arrow line is much bigger than the variance within. Take that like sort of like an average of like three dotted variance, like a green, orange, blue, right? And then basically takes that, like, you take it as a same or not, but it takes that kind of like an average of them, compare against the red line. And then like obviously the variance between is much bigger. Then you can say, oh, you know what? This difference is pretty, significant difference. It doesn't matter like what's the difference is like a 72 to 75 is like a 3 points different or 10 points different. It matter is the ratio of two variances. Okay, so let's take a look at what this really means. So I open the exploratory here, okay, and then like we have this data. We have like 18. This is like a drug test data, so that we have the patient ID. Okay, and what type of the drug were given? So we have three types of things. One is the placebo, which means basically think of it like salt water or something, like there's no drug in there, but a patient take it. And then the drug A and the drug B. And basically like we want to know is like any difference between them, right? So if I go to the chart and then let's say create typical chart here is by the bar chart or something, and then x-axis, and then put the drug, y-axis, I put this is the mood gain. So this is something to do with more like something to do with mood, like what do you call it? Yeah, something about the psychological side of things. Okay, so then I have the mood gain. How so before the we start this trial, the clinical trial, and then like after, like let's say like 2 weeks later or something, how the each patient's mood has changed, and then if it's positively changed or negatively changed, right? And think about a drug for depression or something. So I'm going to, instead of the sum, I'm going to just change that to mean. Okay. And drug A, drug B, and the placebo. And then obviously, like if this is a drug to, make it better for, depression, then, we want to see the drug A performs better than placebo. Drug B performs better than placebo, right? And in this case, even like between drug A and B, and maybe drug B is better than drug A. Okay. So in this case, what we want to know is like, are these differences, some significant? And then, obviously, like we have like, this value looks like in terms of bar chart wise, it's like, seems like there's a difference, but we want to run the test anyway. So in that case, I'm going to the analytics tab, and then like I can select the statistical test from the bottom, a third from the bottom. Under there, we have one-way ANOVA. So I'm going to select that. And the target variable is a mood gain. And the exploratory variable is, in this case, a drug, right? So there are 3 types, and one is a placebo. And then just run the test. And I'm going to hide the left-hand side here. Okay, so this is the result. Okay, and there are a bunch of numbers here, and the important thing is sum of squares and the mean square, F value, P value. If you're familiar with ANOVA, like what you want to see is this P value. If P value is less than, let's take 0.05 or 5% as a threshold value, then less than 0.05 is considered is significant, meaning there's difference among these 3 groups. Okay, but greater than p-value 0.05, then we can say like, there's no significant difference, right? So, but how did p-value, we get this p-value? Okay, we've been talking about ratio between the variance between, variance within. Where are they, right? So I'm gonna just go by one by one to how to get those values in. So here, okay, so this is the same table. I just copy and paste. Okay, and then let's take a look here. Do you remember like I started it as there's a total variance? That's a typical variance, right? Variance in data, but that can be decomposed into 2. One is the variance between, the variance within. The variance between is between, in this case, drug A and B and then placebo. So that's at the top of the row of, it says drug, the column named drug. And it says sum of the squares is 3.45. Okay. And then the next one is, it says residuals. That's the, or sometimes we call it error. And that's the one that basically cannot be explained by this mean. So that means this is actually the variance within. In each group, compared to its own mean, there's still variance. So that being calculated as 1.39 here. And then the purple color is actually the total variance. So when you add the 3.45, something plus 1.39166 something, then it becomes, well, 4.845. Okay. So now that we know what the sum of squares column mean, the next one is what's this degree of freedom? Degree of freedom is basically like how much of the freedom in the component. So for example, like the first row is between. Okay, that means we have a 3 drug, right? I mean, one is drug A, drug B, and another one is placebo. So that means once we know two of them, 2 out of 3, then the last one, like, we don't really have much choice. It's like sort of like once you know 1, 2, and then like the third one, we already know what's going to be the third. So that's the type of the concept of degree of freedom. So in order to calculate the degree of freedom for the variance between, you basically do like a number of groups, in this case 3, and -1 equal 2. And that's the number 2 here. Next one, the degree of freedom of error, or the residuals. And here is the number of rows. In this case, we have 18 patients, and minus number of groups, in this case, 3. So 18 minus 3 equal 15. And then the last one, the degree of freedom, total SS, total sum of square. This is like a combined of between an error. And that is the number of rows in the 18 minus 1. And so this is kind of like similar to variance between. So just do the -1, because when you know the 17 out of 18, there's not much freedom there. So therefore it's 17. Okay. So once we have degree of freedom, basically this is what this one is really doing is in very simple term, it's like basically the number of data. So for example, between, like, we have 3 groups, we can say like there's 3, but it's just like in the degree of freedom world, we have -1 in the 2. Why we need this value? Because what we want to do is we want to get the mean square of error. Mean sum of squares. And you remember, like, when I was talking about the variance and the standard deviation, that time the variance in the precise definition is that we need to actually take the average of those added squared differences. But this sum of square in the left-hand side column, that's actually not the average. That's like added squared values. We haven't taken the average or mean yet. And in order to calculate the mean, we actually not divide it by the original number of rows, for example, between the 3, the error or total can be like 18. We actually take the degree of freedom as a denominator. Okay, so now mean of square is the sum of squares divided by degree of freedom. Therefore, for variance between, mean square is 1.72. Variance error, we have 0.09. Okay, so basically the reason we wanted to get, so this is the typical statistics world. This is the variance, because this is the average of the squared differences. Okay, and once we get this, you remember, like, basically, like, we want to get the ratio. Like if the between is bigger than the error or residuals, or like between is smaller than the error. So that's the F value. So we divide 1.72 divided by 0.09, and that's actually 18.61. And that's what we've been seeing. So here, go back to exploratory. So here, this p value is a division of these two values. Okay, so once we get the 18, so obviously this difference among the means is way bigger than the differences within each group, because it's 18. Now the question is how unlikely to have this value, or maybe like it's very can be explained. I mean, it's kind of like a typical number. So to understand, you can go to the probability distribution tab, and this is this curve line. This is something called F distribution, and then it is showing here is that this white area is like 95% chance like that F value should reside here if the null hypothesis is correct. In this case, again, the null hypothesis, there's no difference among those 3 groups. On the other hand, if the F value resides in this blue shaded area, that's like a 5% area among out of this the area under this F distribution curve. Okay, so if any F value come here or to the right, the farther right, then that can consider as very unlikely. Okay, and this time we got F value 18 point something, 18.6, and that's coming way down here. And then the chance of getting this value or can be go to the farther right is actually 0.000000864. So it's pretty small number. So that means if the null hypothesis is correct, then it's very less likely to get this kind of value because that F value, you remember, it's pretty big. It's like 18 times bigger than this residuals or the variance within. So it's a pretty big number. And then that chance is not going to happen by, just random, variance in the data, variability in the data. So therefore, what we conclude is that in this case, p-value is 0.05, less than 0.05 or less than 5%. Therefore, right-hand side, the statistical value is f, which is 18 this time, 18 point something, and the p-value is less than 5%. So therefore, left-hand side deduction world and the induction world, or world theory and world realities are not consistent. Therefore, we can reject the null hypothesis. Something wrong on this like a hypothesis or some assumption. Then that means we can conclude that there is a significant difference among A, B, and C. Okay, drug A, drug B, and placebo. There's some difference. And then how much of that difference are we talking about? So for now, at this point, what we have found out is there's a difference there. And that difference is significant, but we don't know how much of the difference. And that is something called effect size. And when you, in the same table, we have ETA squared to all the way to the right, omega squared. So these are basically like showing the effect size. Okay. And then for the detail of the effect size, you can actually click on, when you move the mouse here, and there is an eye icon, when you click on it, and you can see what this definition of the metric. But I'm going to just take the eta. I think this is like a Greek word. But anyway, so eta squared. So what this eta squared is actually, this one is a pretty simple one. This is actually the ratio of the variance between, you remember the variance between, or sum of the squares of between, and divided by sum of the squares of total variance. So the variance between divided by variance of total. In precise word, is more like a sum of the squares because it's before taking the average. So it's not precisely the variance, but conceptually to me is like a kind of variance. But in this case, basically comparing these two sum of the squares. Okay, and then we want to see like how much of the ETA. So that means the total sum of squares, the total sort of like a variance, right? So in that data. And out of this, how much of the variance can be explained by this drug variable or between A, B, and C, and difference between A, B, and placebo. Okay, so that's actually presented an ETA square, but also it's actually, you see the same value under the SS ratio column. This is like a sum of squares ratio. And then total is actually 1. And then so in this case, the drug is 0.71 or 71%. 71% of this entire data of the variance can be explained by the drug. So that's really the ETA squared. And then the guidance, we have, I don't even know like who defined this guidance, but in this kind of ANOVA world, people use this as a guidance. And so greater than 0.14 consider as a large effect, and around 0.06, a medium effect, 0.01, the small effect, and so on. So in this case, the ETA squared is a 0.71. It's a huge. So this, if you happen to be writing some report or something like that, then you can say, we find huge, probably huge, a large effect can be found by this drug. Okay. So that's the ETA squared. And then I'm going to skip the omega squared, but omega squared is actually, just to touch briefly, this is not like based on the sample, this is more like based on the population. Therefore, we make the adjustment to the sum of squares. Unlike eta squared, we just use the sum of square, but omega squared, we take the average, or in this case, the degree of freedom. And then we still calculate the variance between, sum of square for the between divided by total sum of square. But we actually, before do the ratio calculation, we make the adjustment with the degree of freedom so that we can see more like that based on the population, not the sample. But anyway, so the omega squared, because of this adjustment, it's more robust compared to eta squared. But both of them basically represent the same kind of type of things. Okay. So the last topic in this ANOVA is a post-hoc analysis. So what's post-hoc analysis? So we have done this ANOVA so far, and we got the p-value, and then we concluded that there's a significant difference among A, B, and placebo. But we don't know where is that difference. Which difference is the one like actually the significant difference? So for example, we have like A, B, C, going back to the school example. Are we talking about A versus B, or A versus C, or A versus C? All of them seems like there's a difference, but which one is actually significant, which one is actually not? And at the end of the day, that's what we want to know for our clinical trial example. Is that like, at least we want to know like the A, B are better than placebo. The next thing we want to know is the A and B, or B is better than A, right? So that question haven't been answered yet. And that's the post-hoc analysis. And what we can do is basically, okay, you know what, like we're going to run a t-test or whatever the statistical test among all the combinations. So A and B, and then A and C, and then B and C. So we can run these 3 tests for these combinations. There's one problem here, and that problem is very severe problem, which is so in this, I found this a cartoon somewhere online. So some people testing, like, jelly beans cause acne, and then the scientists basically try to do the testing. And then they found that there's not much of the difference. So, people taking jelly beans or not taking the jelly beans, there's not much difference. So, okay, there's no, significant difference. But then somebody said, I heard the color actually causes, meaning jelly beans have a green color, red color, blue color, and all that stuff. So the color is the one makes a difference. So they started testing, for example, how about the purple jelly beans and then acne difference, or the brown jelly beans and then see like you get acne or not, or how about the pink jelly beans and then you get acne or not. And they keep testing with all different colors. And so far, like, there's not significant. The p-value is always like greater than 0.05, so you can't reject the null hypothesis. But they didn't stop. They keep testing until they found some tests, some color that produce the p-value less than 0.05. And then they take this result, and the next day they announced it that actually the green jelly beans has something to do with that, you get acne or not. And it turned out this is a really bad practice, but actually some people do in the science world, or especially drug company. But anyway, that's not the subject here. But the problem here is that if we take the 5% as a significant level threshold, right? And then if we can, if we get the p-value that is less than 5%, then we can reject the null hypothesis. So we want to get the p-value less than 5%. The problem is this p-value 5% represent this. If we reject the null hypothesis with this 5% significant level, that means basically like we might be wrong at 5% probability if we reject the null hypothesis. That's what this 5% really means. If we take like a 10% significant level, right? If we get the p-value 10%, and if we reject the null hypothesis, we might be wrong at 10% probability. Same thing, 1% probability or 0.1%. So this is called type 1 error. Type 1 error, again, is by rejecting the null hypothesis, what is the chance that you might be wrong? Okay. And then what happens if we run the test many times, not just one, is that, like, for example, in this case, we have 3 tests, right? So that means that chance of being wrong is 5%, type 1 error, which means 95% we are confident, right? Like 100 times out of 100, 95 times we are correct, okay? So that's that, in that sense, like we are 95% confidence. So we run the test 3 times. What is going to happen is each test, we are 95% confidence, right? So that means every test, like basically if we do the 3 times, and then we're gonna multiply 0.95 3 times, and that becomes 0.857 or 85.7%. So that our confidence level went down to 85.7%. Used to be 95%, but now because we tested 3 times, so the confidence level went down. So that means the type 1 error becomes 14.3% because 1 minus 0.857 or 100% minus 85.7% equal 14.3%. So that means if we reject the null hypothesis at this point, when you do the 3 tests, then the chance of you might be wrong is actually 14% or 15%. That's actually pretty big, right? So that's something like, sort of like the assumption is kind of like now different. And that's why like we need to be very careful, because this means if we run the test 10 times, 1 or 2 out of those tests are actually not significant, but you thought significant, or by rejecting the hypothesis. What happened if not just 3 groups, if you have like 5 groups, or you can go on like 10 groups or 20 groups or whatever, but it's say like 5 groups, A, B, C, D, E. That means you run the test for like 10 times for all the possible combinations. That means the confidence of the 0.95 or 95%, you multiply 10 times, that will become 0.598 or 59.8%, like 60%. And that means type 1 error, 1 minus 60%, 100% minus 60% is 40%. So if you reject the null hypothesis, the chance of you being wrong is actually 40%. It's like almost like 1 in 2 or 1 in 2. Okay, so that's something that's basically kind of like start collapsing your like a whole hypothesis testing assumption here. So that's the problem with this like a post-hoc, something called post-hoc analysis. So you make the adjustment to the p-value. There are multiple ways to do it. Typical ones you often see the Bonferroni, the Holm, or Tukey, and so on. And just take one example, the Bonferroni, how they make the adjustments. They actually make the adjustment. This is very simple. Number of the tests, in this case, for example, like we do the test for 3 times, right? That's, for all possible combination. And so like M becomes 3. And then so basically when you get 0.05, and then you multiply 3, so that becomes 0.15, 15%. So then 15% is the p-value. Now the new p-value becomes 15%. You can't reject it because more than 5%. So it's harder to reject the null hypothesis. So that's the kind of adjustment that you make to the p-value. Let's take a look at here. This one, you actually go to the comparison tab. That's where you see all the combination. So in this case, drug A, drug B, drug A, placebo, drug B, placebo. So 3. And the difference are these here, and the confidence level here. And then the p-value here. And then these are actually the behind the scenes, the t-test is done for all the combinations. So now the method is default the Turkey's HGSD test. That's the default. That itself made already adjustment. So this p-value, the sort of adequate for you to decide you can reject or accept. So in this case, for example, when you see the p-value 0.001, that means less than 0.5%. So you can reject the null hypothesis. That means drug A, B, this difference is significant. But drug A and placebo, that's not significant because 0.31. And then you can change this like different variations here under the property. And then you see a comparison under the method, the default two key. You can apply the Bonferroni. This is the most simple one. Then you do it here, and then like you just multiply 3 to the original p-value because we have like 3 tests. And then, but still, the result wouldn't be much difference here. So 0.001, so therefore you can reject. 0.45, you can't reject. And then the last one, to reject. And what that's really mean is that I think when you go to the means tab, and then, so we now know that difference between A and B is significant. B and placebo is significant, but drug A and placebo are not significant. This chart is showing the mean of each drug plus the confidence interval. Okay, so that's basically this whole ad hoc analysis or multiple comparisons. Okay, so what we have now here, what we have seen is basically we ran the ANOVA. Why we wanted to run the ANOVA? Because often we see the difference in means. In this case, 3 groups, and we know there's a difference among these 3. But is there any difference in here? Meaning, it's really the difference is the important thing, but also their relationship between drug and mood gain. So it depends on what drug you give, the mood gain can change in a significant way. I think that's really we are testing. And in order to find out, you can go to the analytics and then run one-way ANOVA. Then what you want to see is basically the p-value. But the p-value is based on the p-value is a chance of getting this f-value. F-value is calculated as a ratio of this mean square of these two. Like the first one is the variance between, the second one is the variance within. And these mean values are calculated based on the square errors divided by degree of freedom. And the square error is basically the first one is the difference or like variance among these 3 groups. And the second one, residual, is the difference or the variance in each group. Okay, so that's really the ANOVA. And another thing we talked about is that this effect size. So, this indicates the difference is the size of the difference, or how much of the difference is a strong difference or the small difference. And then the last one was the post-hoc analysis. So once we find out there's a difference, meaning there's a relationship between mood gain and the drug, these two, then where is it? Like which combination is the one called making the difference? So we run the test for 3 times. When you run the multiple tests, we have to be careful because the p-value, the meaning of the p-values can change. So therefore, we want to run make the adjustment. In exploratory, by default, we make the adjustment with the 2 key, which is considered as one of the most robust adjustment. But also, you can, if you want, you can change the adjustment as well. Okay, and I think that's pretty much it. Another thing is like ANOVA test has some based on has assumptions. One is a normality assumption, meaning the original data is a normal distribution. And then that test here is being done. And then you can see the result is like a normal assumption is valid. Another valid assumption is a homogeneity test, meaning we have 3 groups. And then the ANOVA test assumes that variance among those, variance of all those 3, basically 3 variances are almost same. So that's another assumptions. So, and then third assumption, there's one more, which is like we have 18 rows, like 18 patients. Those are like independent. So it's not like one part, like the same patients take the same test, in a two, presented in the 2 rows or 3 rows or something like that. But anyway, so this is homogeneity also is the assumption is valid. So when we get this test result, we can take this as a sort of like based on the rigid test. But just this homogeneity test, normality test, though, is that when the data is small like this, we have only 18 patients, then it's actually it's very important to check this type of assumption. If for example, when you go to normality test and a homogeneity test, this test is not valid, then what can you do? Then in that case, you can actually run non-parametric test, which is here classical Walsh test, which doesn't have such assumptions. So you can run that as well. And I have done that seminar in the past. So if you're interested in, please take a look. Okay, so that's it for today. We kind of pass over time, but in the past recording, again, like you can go to our website and under the run, go to training seminar, and then go to the very end of the page. There's a link that says check out the past seminars. Then you can see all the past seminar recording. And here you can find classical Walsh test, which is non-parametric. It's kind of similar to ANOVA, except there are no assumptions. Okay. And also, if you are exploratory users, please make sure or don't forget checking how-to tutorials or how-to videos. And also, we have something called chart gallery. Like if you use chart of the exploratory, this is where like we publish tons of chart related information, how to use the chart, what each chart type means, and what are the each feature of the chart. So it's pretty useful. Okay. So that's it. If you have any question, please feel free to reach out to me at khan@exploratory.io. And also we have the Twitter account @exploratory-data, where we announce, seminar information, product information, and so on. So please check it out. Okay, that's it for today. And thank you so much for joining this seminar. I hope you're gonna have a great rest of the week. All right, see you next week.